calculate the size of a branch circuit for fluorescent lighting, use the total wattage of the tubes multiplied by the number of fixtures, then divide that number by the voltage. This calculation yields the amperage draw of the circuit. With the amperage draw known, appropriate wire size and circuit breaker can be selected. The alternative method involving multiplying the amp draw of the ballast by the number of fixtures isn't accurate because it neglects the power factor of the ballast. Power factor signifies how efficiently a load uses electricity. It varies depending on the load type. Fluorescent ballasts usually have a power factor less than 1, meaning they draw more current than a purely resistive load would. Using the ballast's amp draw can lead to an undersized circuit unable to handle the actual load. To elaborate, the National Electrical Code, or NEC, provides guidelines for electrical installations, including branch circuit sizing. These guidelines aim to ensure safety and prevent overloading circuits, which can lead to overheating, fire hazards, and equipment damage. When dealing with fluorescent lighting, accurately calculating the branch circuit size is crucial to comply with NEC requirements and maintain a safe electrical system. The power factor is a critical consideration in alternating current or AC circuits. It represents the ratio of real power, measured in watts, to apparent power, measured in voltamps. In a purely resistive circuit, the voltage and current are in phase and the power factor is 1. However, in circuits with inductive or capacitive loads, such as fluorescent ballasts, the voltage and current are out of phase, resulting in a power factor less than 1. This means that the circuit draws more current than it would for a purely resistive load with the same real power. The lower the power factor, the more current is required to deliver the same amount of real power. Fluorescent ballasts introduce inductive reactance into the circuit, causing the current to lag behind the voltage. This lag is what reduces the power factor. Ignoring the power factor when calculating branch circuit size can lead to an undersized circuit because the actual current draw is higher than what is indicated by the ballast nameplate amperage alone. The formula to determine the branch circuit amperage for fluorescent lighting is as follows. Firstly, determine the total wattage of all the fluorescent tubes connected to the circuit. This can be found in the tube's label or in the manufacturer's specifications. Secondly, multiply the total wattage by the number of fixtures connected to the circuit. This will give the total wattage of the entire lighting load. Thirdly, divide the total wattage by the voltage of the branch circuit. In North America, common branch circuit voltages are 120 volts, 208 volts, 240 volts, and 277 volts. The result of this division is the amperage draw of the circuit. Once the amperage draw is known, the appropriate wire size can be selected based on the ampacity of the wire. Ampacity is the maximum current a conductor can carry continuously without exceeding its temperature rating. The NEC provides tables, such as Table 310.15b16, which list the ampacities of different wire sizes based on their insulation type and ambient temperature. It is essential to select a wire size with an ampacity equal to or greater than the calculated amperage draw of the circuit. In addition to wire size, the circuit breaker must also be sized appropriately. The circuit breaker protects the circuit from overcurrents which can be caused by short circuits or overloads. The NEC specifies that the circuit breaker should have an amperage rating no greater than the ampacity of the circuit conductors. Standard circuit breaker sizes are 15 amps, 20 amps, 30 amps, and so on. It is important to select a circuit breaker that is appropriate for the calculated amperage draw of the circuit and the ampacity of the wires. For example, if the calculated amperage draw of the circuit is 18 amps, a 20 amp circuit breaker would be suitable, provided the wire size has an ampacity of 20 amps or greater. However, if the calculated amperage draw is 22 amps, a 20 amp circuit breaker would be undersized, and a 30 amp circuit breaker would be required, along with appropriately sized wires. It's also important to consider any voltage drop in the circuit. Voltage drop occurs when the voltage at the end of a long circuit is lower than the voltage at the source. Excessive voltage drop can cause lights to dim, equipment to malfunction, and can even damage equipment. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, use larger wire sizes or reduce the length of the circuit. Calculating voltage drop involves considering the wire size, circuit length, and amperage draw. Online voltage drop calculators can be used to simplify this calculation. Furthermore, when installing fluorescent lighting, it is important to follow all applicable NEC requirements and local electrical codes. These codes provide detailed guidelines for wiring methods, grounding, and other safety measures. A licensed electrician can ensure that the installation is compliant with all applicable codes and standards. In summary, calculating the branch circuit size for fluorescent lighting requires considering the total wattage of the tubes, the number of fixtures, the circuit voltage, and the power factor of the ballasts. Using the correct formula and selecting the appropriate wire size and circuit breaker are essential for ensuring a safe and reliable electrical system. Always consult the NEC and local electrical codes for specific requirements and guidelines, and consider using a licensed electrician for complex installations. To further illustrate this process, let's consider a practical example. Suppose you need to calculate the branch circuit size for 20 fluorescent fixtures, each containing two 40-watt tubes connected to a 120-volt circuit. Firstly, determine the total wattage of each fixture. Each fixture has two 40-watt tubes, so the total wattage per fixture is 2 times 40 watts, which equals 80 watts. Secondly, calculate the total wattage of all the fixtures. There are 20 fixtures, each with 80 watts, so the total wattage is 20 times 80 watts, which equals 1600 watts. Thirdly, divide the total wattage by the voltage to determine the amperage draw. The circuit voltage is 120 volts, so the amperage draw is 1600 watts divided by 120 volts, which equals 13.33 amps. Therefore, the branch circuit will draw 13.33 amps. Next, select the appropriate wire size based on the ampacity of the wire. According to NEC Table 310.15b16, a 14 American wire gauge or AWG copper conductor with type TW insulation has an ampacity of 15 amps, which is sufficient for this circuit. However, it's generally recommended to use a 12 AWG copper conductor, which has an ampacity of 20 amps to provide some safety margin and allow for future expansion. Finally, select the appropriate circuit breaker. Since the calculated amperage draw is 13.33 amps, a 15 amp circuit breaker would be sufficient. However, if a 12 AWG wire is used, a 20 amp circuit breaker can be used, as the wire has an ampacity of 20 amps. It's important to note that this example assumes a unity power factor, which is not the case for fluorescent ballasts. To account for the power factor, the calculated amperage draw should be divided by the power factor of the ballast. For example, if the ballast has a power factor of 0.9, the adjusted amperage draw would be 13.33 amps divided by 0.9, which equals 14.81 amps. In this case, a 15 amp circuit breaker would still be sufficient, but a 20 amp circuit breaker would provide a greater safety margin. In addition to calculating the branch circuit size, it's also important to consider the voltage drop in the circuit. If the circuit is long, the voltage at the end of the circuit may be significantly lower than the voltage at the source, which can cause the lights to dim and reduce the efficiency of the fixtures. To minimize voltage drop, use larger wire sizes or reduce the length of the circuit. The NEC recommends limiting voltage drop to no more than 3% for branch circuits. To calculate the voltage drop in this example, you would need to know the length of the circuit and the wire size. Online voltage drop calculators can be used to simplify this calculation. In conclusion, calculating the branch circuit size for fluorescent lighting involves several steps, including determining the total wattage of the fixtures, calculating the amperage draw, selecting the appropriate wire size and circuit breaker, and considering the power factor and voltage drop. By following these steps and consulting the NEC and local electrical codes, you can ensure a safe and reliable electrical system for your fluorescent lighting installation. Remember to always prioritize safety when working with electricity and consult a licensed electrician if you have any doubts or concerns. Furthermore, understanding the different types of fluorescent ballast can also impact your branch circuit calculations. There are primarily two types of fluorescent ballasts: magnetic and electronic. Magnetic ballasts are older technology and are generally less efficient than electronic ballasts. They also have lower power factors, typically around 0.5 to 0.7. Electronic ballasts, on the other hand, are more efficient and have higher power factors, typically around 0.9 or higher. When using magnetic ballasts, it is particularly important to account for the low power factor when calculating the branch circuit size. The actual current draw can be significantly higher than what is indicated by the ballast nameplate amperage. Using electronic ballast can help reduce the overall current draw and improve the efficiency of the lighting system. In addition to the type of ballast, the ambient temperature can also affect the ampacity of the wires. The NEC provides correction factors for ampacity based on ambient temperature. If the ambient temperature is higher than the temperature rating of the wire, the ampacity must be reduced. This is particularly important in hot environments such as attics or enclosed fixtures. To ensure accurate branch circuit calculations, it's also important to use accurate measurements of the voltage and current. A multimeter can be used to measure the voltage and current in the circuit. It's important to use a multimeter that is rated for the voltage and current being measured. Additionally, it's crucial to understand the different types of wiring methods allowed by the NEC. Common wiring methods include non-metallic sheath cable, or NM cable, electrical metallic tubing, or EMT, and rigid metal conduit, or RMC. Each wiring method has its own advantages and disadvantages, and the choice of wiring method depends on the specific application and local electrical codes. When working with fluorescent lighting, it's also important to consider the grounding requirements. The NEC requires that all metal parts of the lighting fixtures be grounded to provide a path for fault current. This helps protect against electric shock. Grounding can be achieved by connecting a grounding wire to the metal parts of the fixture and connecting the grounding wire to the building's grounding system. In summary, calculating the branch circuit size for fluorescent lighting is a complex process that requires a thorough understanding of electrical principles, the NIC, and local electrical codes. By considering all of the factors discussed above, you can ensure a safe and reliable electrical system for your fluorescent lighting installation. Remember to always prioritize safety when working with electricity and consult a licensed electrician if you have any doubts or concerns. For further clarity, let's examine some common mistakes to avoid when calculating branch circuit sizes for fluorescent lighting. One common mistake is using the wrong voltage for the calculation. It's crucial to use the actual voltage of the circuit, which may be slightly different from the nominal voltage. For example, a nominal 120 volt circuit may actually operate at 115 volts or 125 volts. Using the wrong voltage can lead to an inaccurate amperage calculation. Another common mistake is neglecting to account for the power factor of the ballasts. As discussed earlier, fluorescent ballasts have a power factor less than 1, which means that they draw more current than a purely resistive load would. Ignoring the power factor can lead to an undersized circuit. Another mistake is using the wrong ampacity for the wires. The ampacity of a wire depends on its size, insulation type, and ambient temperature. Using the wrong ampacity can lead to overheating and potentially a fire hazard. It's important to consult the NEC tables to determine the correct opacity for the wires being used. Another mistake is using the wrong size circuit breaker. The circuit breaker should be sized to protect the wires from overcurrents. Using the wrong size circuit breaker can lead to nuisance tripping or, in the worst case, a fire. The NEC specifies the maximum size circuit breaker that can be used for a given wire size. Another mistake is failing to consider the voltage drop in the circuit. Excessive voltage drop can cause lights to dim, equipment to malfunction, and can even damage equipment. It's important to calculate the voltage drop and ensure that it is within acceptable limits. Another mistake is not following the NEC and local electrical codes. The NEC provides detailed guidelines for electrical installations, and local electrical codes may have additional requirements. It's important to be familiar with these codes and follow them carefully. Avoiding these common mistakes can help ensure a safe and reliable electrical system for your fluorescent lighting installation. Always double-check your calculations and consult a licensed electrician if you have any doubts or concerns. To expand upon the concept of power factor correction, it's important to understand that utilities often charge commercial and industrial customers based on their power factor. A low power factor increases the overall current draw on the electrical grid, which can lead to increased losses and reduced efficiency. To encourage customers to improve their power factor, utilities may offer incentives for installing power factor correction equipment, such as capacitors. Capacitors can be used to offset the inductive reactance of fluorescent ballasts and other inductive loads, thereby improving the power factor. By improving the power factor, customers can reduce their electricity bills and improve the efficiency of their electrical systems. Power factor correction is typically implemented at the service entrance of a building or at individual loads with low power factors. The size of the capacitors required for power factor correction depends on the amount of inductive reactance in the circuit. Electrical engineers can perform calculations to determine the appropriate size of capacitors for a given application. In addition to capacitors, other methods can be used to improve the power factor, such as using synchronous motors or active power factor correction circuits. Synchronous motors can be operated in an overexcited state, which generates reactive power that can offset the inductive reactance of other loads. Active power factor correction circuits use electronic components to shape the current waveform and improve the power factor. These circuits are commonly used in electronic devices, such as computers and televisions. Improving the power factor not only reduces electricity bills but also improves the overall stability and reliability of the electrical grid. A higher power factor reduces the current draw on the grid, which reduces the load on transformers and other electrical equipment. This can extend the life of the equipment and reduce the risk of failures. In summary, power factor correction is an important aspect of electrical system design and operation. By improving the power factor, customers can reduce their electricity bills, improve the efficiency of their electrical systems, and improve the stability and reliability of the electrical grid. Always consult a qualified electrical engineer for power factor correction applications. Finally, let's consider the impact of LED lighting on branch circuit calculations. LED lighting has become increasingly popular in recent years due to its high efficiency, long lifespan, and reduced energy consumption. LED fixtures typically use significantly less power than fluorescent fixtures, which can reduce the load on branch circuits. When replacing fluorescent fixtures with LED fixtures, it's important to recalculate the branch circuit size to ensure that it is still appropriate. In many cases, the existing branch circuit can handle the reduced load of the LED fixtures without any modifications. However, it's still important to verify that the wire size and circuit breaker are adequate for the new load. LED fixtures also have a power factor, which should be considered when calculating the branch circuit size. However, most LED fixtures have a high power factor, typically around 0.9 or higher, so the impact of the power factor is usually less significant than with fluorescent fixtures. In addition to reducing the load on branch circuits, LED lighting also offers other benefits, such as improved light quality, reduced maintenance costs, and increased control over lighting levels. LED fixtures can be dimmed and controlled using various control systems, such as dolly or 0 to 10 volt domain. This allows for greater flexibility and energy savings. When installing LED lighting, it's important to follow the manufacturer's instructions and all applicable NEC requirements and local electrical codes. LED fixtures should be properly grounded and wired according to the code. In summary, LED lighting offers significant advantages over fluorescent lighting, including reduced energy consumption, longer lifespan, and improved light quality. When replacing fluorescent fixtures with LED fixtures, it's important to recalculate the branch circuit size and ensure that the wire size and circuit breaker are adequate for the new load. Always follow the manufacturer's instructions and all applicable NEC requirements and local electrical codes. Remember that electrical work can be dangerous, and it's always best to consult a qualified electrician if you have any doubts or concerns. Safety should always be the top priority when working with electricity.